Good evening, 12th graders. Alright, so today what we're doing is we're moving on to section 7.5, in which we're going to start learning some applications for differentiation. In particular, in section 7.5, we're going to talk about applications of the first derivative of a function, and then we'll move on and we'll learn applications of the second derivative of a function at a later time. And there are two types of applications in particular that we're going to be looking at within section 7.5. In this video, we're going to focus on learning goal 1, which says that you will be able to find an average rate of change and an instantaneous rate of change of one variable with respect to another variable. So we're looking at an average rate of change and an instantaneous rate of change. Alright, and then in the next video, we'll look at motion along a straight line, in which you will be able to analyze an object that is in motion along a straight line. There we go. Well, let's try this out. The first thing that I want to talk about with you when we're discussing rates of change is simply how slope is a rate of change. And I've got a couple of graphs that I want to look at to explain that idea of how the slope of a function represents a rate of change. Alright, now you look at this graph, which is relating someone's bank balance to how many months their money has been in the bank. And what I'm going to do is I'm going to try to find out what the average rate of change is for this particular bank account. Now you'll notice that this balance has a linear function to model the balance over time. That's not common, but nevertheless it works right here. And what you can tell for the selection that I made is that this bank account, let's go back to that graph. This bank account lost $400, so the change is negative 400 over a period of 8 months, August being the 8th month, over 8 months. And so what this graph shows is that every month this bank account loses $50 on average. The rate of change is negative $50 per month. Okay, so dollars per month, that's a rate of change. Let me give you another example of how a slope represents a rate of change. Let's take a look at this graph, which is comparing the velocity of an object in motion. The velocity of an object in motion with how long it's been in motion. Okay, well, if I wanted to look at the rate of change for this curve, what I'm actually going to be able to do is find the slope of a secant line. And you can see the secant line that I drew right there. And this is going to help me find what's called an average rate of change. And what it's going to tell me is that if I look over a certain time frame, I'm going from 1 second to 7 seconds, so if I look over a 6 second time frame, the velocity changed from 7 to 10, changed by 3 meters per second. Okay, and so the rate of change here every 1 second then, the velocity would increase on average by a half meter per second. So it's 0.5 meters per second or 0.5 meters per second squared. Alright, for those of you taking physics, you might recognize that whenever we found that average rate of change in velocity, that slope, that rate of change ended up being an acceleration measurement. But the point is, you're saying what is the change in y compared with the change in x, and how much does y change for every single unit that x changes. That's what slope represents, and that's how you find a rate of change. Okay, now let's look at a specific problem. Now there's just another rate of change that I could have found with that same graph. We're going to look at this, where it says if a rock is dropped from a height of 50 meters, its height is given by the position function s equals negative 4.9t squared plus 4.9t plus 25. And what we're going to do first with this is we're going to find the average velocity of the rock over two different time intervals. We're going to find out what is the average velocity of the rock from 0 second to 1 second, as well as what is the average velocity of the rock from the 1 second to the 2 second mark. Okay, now I need to explain how in the world we're going to find velocity from what's called a position function. Okay, now look at the graph right here. When I'm talking about position, which is what S represents here, what I'm talking about is in relation to a starting point, where is this rock located? And since we're talking about that being a height position, the rock can either be above or below where it started from. Now, the units for that position are going to be meters. And then the time, of course, is going to be measured in seconds. And so whenever we find a rate of change here, that rate is going to be in meters per second. And whenever you measure something in meters per second, it's going to be velocity. Okay, well, let's go ahead and put that into practice then. And so what we're going to do then is we're going to find the average velocity of that rock on the interval from 0 seconds to 1 second. In other words, we're going to find its average velocity from when it was released at 0 seconds to 1 second after it was released. Now you need to know this, that any time you're trying to find an average rate of change, what you're trying to do is on average see what is the change in y in relation to the change in x. And so we often represent that with delta y over delta x. Okay? And so another way of looking at that is that's the final y value minus the initial y value divided by the final x value divided by the initial x value. All right, final y minus initial y over final x minus initial x. Let's do that for this particular function then. Delta y over delta x. Well, that means that what we need to do then is we need to find out what f, or it was s actually, of 1 is. What was the position of this rock after 1 second? And we'll subtract the position of the rock initially after 0 seconds. Okay, that'll represent our change in y. And then we're going to divide that by the change in x. And we change from 0 seconds to 1 second, so 1 minus 0. Now you can use your calculator to figure out what s of 1 and s of 0 are. You see the equation on your screen. If you want to take a moment to do that, great. I'm going to go ahead and write the values on the screen. It turns out that after 1 second, this rock is 25 meters above the ground, which coincidentally is also what s of 0 is equal to. So after 1 second, this rock is right back where it started in terms of its height above the ground. Although you can see that the rock started off going up and then came back down, it just took exactly 1 second for it to get right back where it started. Alright, and we're dividing that by 1 minus 0. Well, this is going to be 0 over 1, or just 0. On average, from 0 to 1 second, the velocity of this rock didn't change at all. It stayed the same. It was 0, and that would be in meters per second. Now let's look at the average rate of change in the velocity of the rock from 1 second to 2 seconds. So if we're going to find the change in y, that means we're going to find out what s of 2 minus s of 1 is for that time interval. And then the change in x, or the change in time in this case, we're going from 1 second to 2 seconds, so we'll do 2 minus 1, the final minus the initial. Okay, now I've already plugged in s of 2 and happen to know that at 2 seconds, the height of this rock is 15.2 meters. And we already said that it was at 25 meters after 1 second, so we'll subtract that over 2 minus 1, which is 1. And 15.2 minus 25 is negative 9.8. Negative 9.8 divided by 1 is negative 9.8. Now you might think, how in the world is the velocity negative? Well, the velocity being negative 9.8 meters per second, the negative part just indicates that this rock was going down at that time. Because the position, if it was positive, was going up, and if it was negative, that means it was going down. So on that interval from 1 to 2, the average rate of change was negative 9.8 meters per second. I'd like to take a moment to summarize what it is that you're doing whenever you find the average rate of change. We've already talked about how when you find the average rate of change, you're finding the change in y over the change in x. But in terms of calculus, what we're actually doing is we're finding the slope of the secant line from the initial point on the graph to the terminal point on the graph for the interval that you're looking at. All right, so we found the slope of the secant between when the time was equal to 1 and the time was equal to 2. And always when you're trying to find an average rate of change, you're trying to find the slope of the secant line connecting the 2 points on the interval you're looking at. That needs to be compared with what you do when you try to find an instantaneous rate of change. So that's the next concept for us to discuss, is instantaneous rate of change. All right, so now we're going to take that same function and we're looking at instantaneous rate of change. This is supposed to be part B of the example, not part A of the example, where we're going to find the instantaneous velocity of the rock at the given times. Okay, now this graph is still comparing meters to second, and we're still going to be finding a slope whenever we're trying to find the instantaneous velocity instead of the average velocity or the average rate of change. All right, but the difference here is that when you're trying to find the instantaneous velocity for a certain value, what you're going to do is you're going to find the slope of the tangent line to that graph for that particular value. In other words, when you're trying to find instantaneous velocity, you're no longer doing delta y over delta x. What you're doing is you're finding f prime of whatever x value it is that you're working with. Or, in this case, where we're working with s's and t's, to find the instantaneous velocity of the rock at the times t equals 1 and t equals 2, what we're going to do is we're going to find s prime of 1, and then we're going to find s prime of 2. Fairly straightforward. All right, let's go ahead and do that. In order to find s prime of 1 and s prime of 2, of course, we need to know what s prime of the original function is. And so let's go and differentiate right now. This one's a fairly simple one to differentiate. We're going to get negative 9.8t plus 4.9. All right, tough to make that little decimal right there. And what that function is going to tell us is what the instantaneous velocity is for any time that we choose to input. And what we are choosing to input are 1 second and 2 seconds respectively. So let's find out what s prime of 1 is. That would of course be negative 9.8 times 1 plus 4.9. And that is going to equal negative 4.9, and since it is a velocity here that we ended up finding, the units will be in meters per second. Now remember that you can write meters per second the way that I wrote it, or you can write it as meters times seconds to the negative first power. Because if you apply your rules for negative exponents, that s will go to the denominator, and then it's still meters per second. Okay, now let's look back at the graph and see how much sense that makes. We just said that for when at t equals 1, the instantaneous rate of change is negative 4.9 meters per second, which means when we go to 1 on the graph, that the slope of the tangent at that point is negative 4.9, and that was in meters per second. There's our instantaneous velocity. And then what we're getting ready to do is to find out what the instantaneous velocity is when t is equal to 2. So we're going to find out another tangent, and you can see that we're going to expect this to be a steeper slope. So we're going to expect a more negative number, so to speak. So what 2 seconds in? S prime of 2 going to be negative 9.8 times 2 plus 4.9, and that is going to be equal to negative 19.6 plus 4.9, which turns out to be negative 14.7. So the velocity was faster at t equals 2. Don't you expect an object that's falling to gain speed over time? That makes sense. And again, the negative part just means that it's going downward because that was a position graph, and down on the position graph meant that the object was falling downward. All right, I want to summarize here. When you're trying to find an average rate of change, you're always trying to find the slope of a secant line on some interval a to b. All right, the slope of a secant line on some interval a to b, and that's basically equal to the change in the y-coordinates between points a and b, and then the change in the x-coordinates between points a and b, or b minus a in other words. Whereas when you're trying to find an instantaneous rate of change, all you're trying to do is try to find the slope of the tangent at some value a, or you're trying to find f prime of a. There you go. Now you know how to find an average rate of change and an instantaneous rate of change. We'll put this into practice more in class. If you haven't tried numbers 1 and 2 from exercise set 7N, I believe, then you ought to take a look at those, and we'll continue to do some more within class tomorrow.